welcome back. In the last lecture, we asked ourselves that what is going to be the analog of the Fejer kernel in R. So, by following what information we have from the circle case, Fourier series case, define f of r for some positive r. This is equal to r sin pi x r square divided by pi x r square if x is not equal to 0 and is equal to r if x is equal to 0. This is the analog of the Fejer kernel, and we are just copying it what we have there in the series, only with the n part. Now, we have for r positive real number. Okay. Now, why Fejer kernel was important? Because it has some nice property, and through that property we were able to get back our function by knowing the Fourier coefficient, and that is through the what we have learned there. If f is a 2 pi periodic function and if we assume it to be continuous, then f convolution of k n, there we denoted the Fejer kernel, this converges to f uniformly in the Fourier series case. So, what properties of the Fejer kernel there worked? One thing is that they are non-negative. The integral over the period of 2 pi, then that was going to give us 1, and then away from 0, the integral of the Fejer kernel, which as n goes to infinity, this goes to 0, which means this is the picture what we had done is for 2 pi periodic function. So, now this is some 2 n plus 1, this is a positive function or negative function, and away as n goes large and large, this portion, the area is going to contribute very little. That is what made wonder to get back f from f convolution of k n, which is in the form of 1 minus mod z by n f hat of n e to the power I n x. Now, let us see that similar kind of property, whether this holds here for our Fejer kernel or not. Unless and until that happens, then there is no reason to call this as the Fejer kernel for R in R. Okay. So, the first thing first, clearly f r of x is greater or equal to 0. Now, we would like to see what is the integral of dx. This is equal to r times minus infinity to infinity sin pi r x square divided by pi r x square dx. Now, make a change of variable. You take pi r x to be y. Therefore, this is 1 over pi minus infinity to infinity sin y by y whole square dy. And we know that, I mean, what is the value of this, that is pi. So, this which is equal to 1. So, this to compute this integral, this is well known, and we must have encountered it earlier. Otherwise, one hand waving argument is that if you define, let us say I t, this is equal to minus infinity to infinity sin t y by y whole square dy, and then you take I prime t, then this is going to give us basically, now assuming everything fine formally we can by doing hand over. So, this is going to be sin 2 t x by x dx. So, if we make a change of variable, I mean, so then at you will get that I t is equal to pi a plus some constant. So, therefore, this is equal to pi, a equal to t equal to 1, you will get that this is pi. Okay. So, what we are essentially, this integral is a known integral which takes the value pi. Now, third property what we need to see is that if I am going away from 0, then if I take my r to be large enough, then the integral of f r x should vanish. That means, is limit r goes to infinity integral mod y greater than delta f r of y dy is equal to 0 true, because that is one of the most fundamental property what we have used in the Fejer kernel business in the Fourier series. So, let us compute this. Let delta greater than 0. So, now this is limit r goes to infinity. So, let us do this mod of x greater than delta, this is 1 by r, then pi square sin square pi r x divided by x square dx, that is what the Fejer kernel is. Now, this one is lesser equal to 1 over pi square r mod x greater than delta sin square pi x is always bounded by 1. So, I have dx by x square. Now, away from the origin dx by x square, this is a finite number integral delta to infinity 1 over x square is minus 1 over x from delta to infinity. So, this is nothing but 1 over delta, and delta is positive. So, this is some constant times 1 over r into 1 over delta. So, this goes to 0 as r goes to infinity. Therefore, this property of the Fejer kernel is also true. So, hence, f is a continuous function, f is if continuous moderate decay. What we have seen is that f is will be uniformly continuous, then f convolution of f r, this converges to f uniformly. Exactly, if we follow the same method, just to recall what it is. So, f convolution of f r of x minus of f x. So, this is we can write that this is integral of f of x minus of y, f r of y dy, and minus f x into 1 in place of 1, I can write that this is f. This is the technique what we used in the Fourier series case. So, this is lesser equal to minus infinity to infinity mod of f of x minus of y minus f of x and then f r of y dy. Now, as f is continuous, therefore, for epsilon positive it is uniformly continuous. So, epsilon positive there exists a delta greater than 0 such that mod of f of x minus of y minus of f of x is less than epsilon whenever mod y is less than delta. So, therefore, this integral I can bracket it into mod y less than delta plus mod y greater or equal to delta. Now, on the first one uses the continuity of f, uniform continuity, pull out the epsilon, we left with the integral of f r, which value is 1. Now, in this case, as r goes to infinity, we know that this is nothing but I will pull out now the second part. So, this is less than epsilon plus the second part I will pull out 2 times supremum over mod of f of x such that x belongs to R, because this is a bounded function and we are left with and just by the third property this goes to 0 as R goes to infinity. Exactly the same proof works if for this Fejer kernel, if our f has moderate decay and continuous. Okay, so there you know the Fejer kernel, there it was looking as f convolution of f n in the series case is equal to summation over minus n to n 1 minus mod j by n f hat of n e to the power 2 pi I n x. So, this is what was the Fejer kernel convolution was looking like. So, natural to see if we are talking about the analog, then whether this is going to be true here in this case or not. So, for that let us do try to see that what will be the analog. The sum would be integral minus r to r, then 1 minus mod xi to the by r, then this is f hat of xi and e to the power 2 pi I xi x dj. We must look that this is f convolution of f r in our case. Okay. So, we compute this integral minus 2 pi I xi x dx. There are two x symbol. So, we will take this out, we will put that y xi y dy and e to the power 2 pi I xi x dj. Now, our functions are nice. So, we can interchange the integral. So, this is going to be minus infinity to infinity f of y, then integral minus r to r 1 minus mod xi by r e to the power 2 pi I x xi x minus of y, then this is dj integral, then we have left with dy. So, now essentially what we need to, if we can show that this is f r, if this is equal to f r of x minus of y, then we can write this as f convolution of capital F r at x. Okay. So, that essentially asks us to compute minus of r to r 1 minus mod xi by r e to the power 2 pi I xi x dj. This obviously mod is there, we want to get rid of that. We will get it is 1 minus xi by r e to the power 2 pi I xi x dj, and here this is minus of r to 0 1 plus xi by r e to the power 2 pi I xi x dj. Now, just compute this integral, then this is the first one would be e to the power 2 pi I xi 2 pi I x xi divided by 2 pi I x, which is evaluated at 0 to r. So, now this we can write that this is r minus of 1 at 0, this is going to give minus of 1 if I compute with this. Then obviously, we are going to do the integration by parts in the next. So, now in the integration by parts, the 0 part will get killed. Therefore, what we get here minus r e to the power 2 pi I r x divided by 2 pi I x, and then 1 over r is there, 1 over r, and then plus then the integral over 0 to r e to the power 2 pi I xi x by 2 pi I x into derivative of this is dj. So, this we can write this as, if we do the integral again. So, this and then the plus the other one is going to be exactly the same thing, which would give 1 minus e to the power minus 2 pi I x r divided by 2 pi I x, and then minus e to the power. So, this quantity is e to the power minus, this is minus of r e to the power minus 2 pi I r x by 2 pi I x, and a factor of r is also there, plus the integral minus r to 0 e to the power 2 pi I xi x divided by 2 pi I x square, then this is 2 pi I x, then this is d j. Now, as you can see, this and this gets cancelled. So, I have here 1 minus 1 by 2 pi I x, here 1 by 2 pi I x, this gets cancelled. Then this term and then this term, they also get cancelled. So, what we need to evaluate only this. So, now this is going to be e to the power 2 pi I j x divided by 2 pi I x square, and then at this is from 0 to r, and then this one is e to the power, this is minus, this is plus e to the power 2 pi I x xi divided by 2 pi I x square, then minus r to r 0. So, if we compute this, then this is going to give us e to the power. So, let us write it on the next page. This is going to be equal to e to the power 2 pi I r x plus e to the power minus 2 pi I r x minus of 2, minus 1 is 2, and then this is r times 2 pi I x square. So, this is going to be, of course, this is 2 cos 2 pi r x minus 2 by minus 4 r pi x square. Now, this is equal to 1 minus cos 2 x is 2 sin square x. So, now this is minus of 4 sin square pi r x divided by minus 4 r pi x square. This is nothing but r times sin square pi r x divided by pi x square, if x is not equal to 0, because we are dividing it by x, we are assuming that x is not equal to 0. Now, if you take that if x is equal to 0, then you are left with x equal to 0, then minus r to r 1 minus mod xi by r and d xi, this obviously you will get r. So, now what you have got, minus r to r 1 minus mod xi by r f hat of xi e to the power 2 pi I j x d j. This is nothing but, so we have a concrete analogy with the Fourier series. Okay, so now successfully we have done this the Fejer kernel. So, actually what we have seen, I mean, we can expect if inversion when we have f hat, we are assuming f hat to have moderate decay. So, it is natural to think about what are the a large class of function in which we can do our Fourier analysis in a very successful way. So, in the next lecture, what we will do is that we will compute the Fourier transform of some nice function, and then by looking at the behavior we will kind of will decide that what kind of space we are looking for. Thank you.